Hey everybody, welcome to part 2 of the Algebra 2 Semester 1 review. We're in part 2. We're going to be doing questions 21 through 38, or the rest of the packet right here, right now. I'm going to be honest right now also that a lot of these questions are maybe I would call superfluous, I guess, to actually, I have no idea how to spell superfluous. Superflu. Is that really it? Superfluous. I've never seen that in the crossword. It is a crossword word though. It has a lot of vowels. Anyway, yeah, a lot of these questions aren't going to necessarily be needed exactly on the final, but the bits and pieces of them and like knowing the logic behind them might be useful. And really this is to cover everything in the semester. So if you feel good on these questions, I guarantee you'll feel fine on the final as well. Let's just get started. I also want to apologize too that I'm recording this at school, so my recording setup is a little more scuffed than I guess a little normal. The only thing that's maybe going to be annoying is that I'm recording on the thing I'm writing on, right? So you're going to hear this sort of clicky clacky a little bit, which, you know, it's like a little bit of ASMR. So not a bad way to start your day, or well, at least I'm starting my day with this. Not a bad way to end your day, maybe. Just some math ASMR. Anyway, load up the Subway Surfers, load up the Family Guy. Let's get into some practice problems. So this one, we've done quite a few of. This was like the beginning of our graphing polynomials unit. And these, you kind of just have to know the facts of the situation, what's going on, and how to sort of read this polynomial and understand the information from it. And then you actually have to graph it based on what you know about this this polynomial. So first things first, we have this degree box. And I'm going to go kind of hard on this one. I'm going to define some things. So degree is the highest exponent above a variable. Okay. And that's in standard form, technically. But really, that's the same thing as what's going on here. We did the Jeopardy review yesterday, and when I put up a polynomial, which we'll see a couple problems in the future, an example of this, but a lot of people are just adding up the exponents, which is actually what you do for these ones because they're in factored form. So in standard form, you just count the highest exponent above a variable because everything's already multiplied out. But if I think about these factored forms, these exponents right here, these are the ones that are going to tell me how many times I'm multiplying an x together, right? If I multiplied this out, I would end up with an x squared. If I multiplied this out, I would end up with an x to the fourth. These are also being multiplied, and so I would end up with x to the sixth. So this is a sixth degree polynomial because in factored form, so anytime you have these sort of multiplying sets of parentheses together, the degree is the exponents added. Time for class. And then the number of possible real roots, well, that's just always equal to the degree. So it's 6. There are 6 possible real roots. In this case, we won't have that many, but the degree basically talks about how many possible zeros there would be. Like one theoretical way to write this would be, 6 polynomials, 6 x minus 7, 6 times, right? That would be an example of a 6th degree polynomial that has 6 roots, okay? To find the y-intercepts, you plug in 0 for x, and then you solve, right? It should just be some number. You can type it into a calculator. Be careful with your exponents in the parentheses. So for example, in this problem, to calculate the y-intercept, I'd really be taking, if x was 0 in this first one, I'd just have -3 squared, and then times -1 to the fourth. Be careful when you type this into a calculator. If you don't use parentheses, your calculator only does what it says, and it'll read the exponent first before the minus sign. But really what this means is -3 times -3, which is actually +9, right? So a negative times a negative is a positive. And then same thing here. This is -1 times -1 times -1 times -1. That's a bunch of negatives, but it's an even amount of negatives. So really I'm multiplying -1 times -1 is +1, -1 times -1 is +1, +1 times +1 is +1. Anyway, it's just 9 times 1, which is 9. Okay, so the y-intercept is going to be at 9. I can go ahead and plot that on my graph already. I know when x is 0, y is going to be up here at 9. Okay. And then we get to zeros in their multiplicity. To find these, we have to look at the factors, right? The sets of parentheses, and we figure out what values of x make the equation equal to 0. That's why we call it a 0, right? Anytime that x makes the output 0, that means we are on the x-axis, which is like an x-intercept or a 0, okay? So this x minus 3 term, x minus 3 quantity squared, this is going to tell me that there's a 0 when the value of x makes this thing 0, which means it's at x equals +3, okay? Really what you're doing is you're applying the 0 product property. It's the value of x that turns either of the sets of parentheses into 0 because you're multiplying them. And then their multiplicity is just the exponent above it. So it has multiplicity. I'm going to go mult period to shorten it. It has multiplicity 2, okay? And then the only other thing that you have to know about this is based on its multiplicity, what does it do when it hits the axis, okay? And maybe you want to write this as a little aside. So I'm going to go, I guess, right here underneath. I'm going to say, note about multiplicity. So for multiplicity, if the multiplicity is even, it will bounce off of the axis, right? It'll hit the axis and then bounce back up. The way to remember that, obviously, even Stephen Harvey sit on it, which is like bouncing. If you remember that TikTok from like a few months ago at this point. It was really relevant when I said it the first time, so I think it was really funny, but that TikTok sound isn't around anymore. Anyway, so then the other way is that if it's odd, meaning it's like multiplicity 1 or 3 or 5, it's going to cross through the axis, right? It's not going to bounce through it, it's just going to cross through it. So you have two options, bounce or cross. And in this case, because the multiplicity is 2, I'm going to bounce. Okay, so I can put that down. I know I can put a point at x equals +3. It's right here, I say. And that is, I'll just do it in green. Make my whole graph green. That's 3, 0, and I know that it's going to bounce there. Okay. The other 0 happens when this polynomial turns to 0. Okay, which means there's a 0 at +1 as well. X equals +1. It has a multiplicity of 4, so it's going to bounce as well. So that means there's another point, let's say about right here, at 1, 0, that is going to bounce. Okay. Well, this is a little interesting because I have to hit all 3 of these points, right? I have to think about the way that I could bounce off of both of these axes, or both of these points on my axis, and cross through 0, 9. But since I have no zeros over here, there's no way I can start down here. Because if I started down here, I'd have to cross through at some point. So that doesn't work, which means I must be starting up top. Okay. And then I cross through my y-axis. Let me redraw this a little bit better. I cross through my y-axis at my y-intercept. And then when I come down to my first 0, I bounce off of it. And then at some point, I have to come back down to hit my second 0. And so I'm just going to come back down. And then once I hit this one, I also bounce again. So really, I look like this W. Okay. So that's a good sketch of my polynomial. It's not great. Like, look at my slope over here. It's being weird, but close enough. Okay. And so for the end behavior, you have two options. Either you can think about the odd degree versus even degree and then the leading coefficient, or you can sort of draw your graph. There should only be one way to draw your graph, and then use your knowledge of the graph to use your end behavior. So once again, what this means is as x goes to negative infinity, that's all the way to the left. So this is as far left as I can go. When I'm at my furthest left point, what's my function doing? Where is it at? And it's continuing upwards this way, right? So as my x, as my left and right goes to the left, my up and down, my f of x is going to be going up to positive infinity, okay? And then same thing over here as x goes to the right. In this case, once again, as I continue on to the right, my graph is continuing upward, so f of x must also be going to infinity, okay? You can also know this, and I don't know if you'll have room for this sort of thing on right here at least, but let me show you a little table that can help you with end behavior. Okay, so I'll have this one be odd degree. So this is odd degree. This one will be even degree. And then this one will be negative leading coefficient. So I'll say negative A, negative, oh, go away weather, negative A, and then positive A, and positive A, okay? So what that means is when I have a leading negative coefficient, so like in front of all my parentheses is a negative or something, then and an odd degree, that means I'm going to have the same end behavior as this line. Okay, so generally my line's going to follow this pattern. There's going to be more squiggles in between, but that's kind of it. And then vice versa for the odd with a positive, it's going to have like a positive slope. If you think about it, linear functions are odd degree, and so the end behaviors of them are all the same as any higher odd degree. And so a negative linear function goes down like this, and a positive linear function goes up like this. Every other higher degree function has the same end behavior. And then the smallest even degree that we know is a parabola. And so the parabolas go like this, or an even, negative leading coefficient even will have this end behavior. There might be more bounces or squiggles in between as well. And then this one, same thing. As you go up on both sides, or as you go to the left, you go up. As you go to the right, you go up. And that's what we had here. We had a positive leading coefficient with an even degree. So we had this end behavior, which was this. Okay? Anyway, so that's pretty in-depth, but these are good notes to have because you will have to do a problem like this. Let's practice with another one. So this time I can see that I have a leading negative coefficient, or a negative leading coefficient. Negative leading coef, okay? So that's going to change what my graph looks like. But first, let's just talk about the degree. In this case, I'm just going to add up all my exponents because I'm in factored form. And so this 2 plus this 1, this one's kind of hidden, right? But it's anything by itself is just to the first power. So this is degree 3 because 2 plus 1 is 3. That means that there's 3 possible real roots. Sorry for my email. And the y-intercept we find by plugging in y equals 0, or x equals 0. Okay. Here we go. So all I'm going to do is just keep everything the same except for don't write the x's because they're equal to 0 now. And I get negative 1 times 1 times negative 5. Well, negative 1 times 1 squared. 1 squared is just 1. So negative 1 times 1 is negative 1 times negative 5 is positive 5. So that's my y-intercept. So I know when x is 0, y is 5. Okay. And then let's go to the zeros and their multiplicities. So I have 1 at x plus 1, quantity squared. That tells me that there's a 0 at x equals a negative 2, right? That's the value of x negative 2, where did I get that? Negative 1. That's the value of x that makes this whole set of parentheses 0. It has a multiplicity of 2. So that means that it's going to bounce. So I have a point at negative 1. Swoop. It's negative 1 comma 0, and I'm going to bounce there. Okay. And then my other 0, x minus 5 to the first power. That means there's a 0 at x equals 5 with a multiplicity of 1 this time. And because that is odd, that's an odd multiplicity, that means I'm going to cross through. So at positive 5 in the x, just like here, I guess, 5 comma 0, I'm going to cross through. Okay? So if we think about it, I know that I have to bounce off of this, come back up and go through this, and then cross through like this. And so I can already imagine that my graph, because I can't cross through anything to the left of this, that means I have to start up top, go through my first 0 and bounce, then bounce up to my y-intercepts, and then cross through my second 0, which looks like this function. Which, hey, if we go back to our last page, this is an odd degree, negative leading, so odd degree negative coefficient, that has the same end behavior as a negative linear function, right? As x goes to the left, my output's actually going up to positive infinity. And then as x goes to the right, my output is actually going down to negative infinity. So it's opposite what you would normally do, right? Or it's opposite of what x is doing because it's negative. Okay, cool. Let's keep going. So here's the example I was talking about a couple minutes ago, I guess, about how to find the degree in standard form. So these are standard. I know that they're standard form because I have no parentheses. I have all my terms just being added or subtracted together, and everything's like coefficient x power, right? That's standard form. That's also how the definition of polynomial will go for in a second. But in this case, you just look for the highest degree. Technically, we do say leading coefficient, which implies that it's the first one. It doesn't have to be, but technically, in order for it to be perfect standard form, you have to write your largest degree first. So in this case, both of these are. My largest degree is 9, so this is just degree 9. Or my largest exponent is 9. Wait, what did I say? Highest degree? I guess that makes sense, but really I'm saying highest exponent above variable. And then to determine the degree of this polynomial, there's a 7 right here, so this is degree 7. Nice, okay. And then determine whether each of these is a polynomial. We did talk about this on, I think, on like the first day we talked about polynomials, but here's the definition real quick. Mathematically, it looks like this. Anything f of x where you have this a times x to the n plus b times x to the n minus 1 plus dot 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 plus, oh wait, you say a1, a2. a1, a2 plus a to the n x to the n minus, I don't know, actually. It would just be a to the n times x. Oh yeah, a to the n times x plus a to the n. Oh wait, a to the n minus 1. Anyway, okay, so what I'm saying is all of your things have to look like this. It has to be f of x equals or y equals coefficient variable power, all positive, okay, for the exponents. So I can't have any fractions exponents. So I can't have anything that is like any x's in a denominator, so no rational functions. And then I have to make sure that all my powers are positive as well. So in this case, this one is yes, because there's no negative powers and all powers are whole numbers. Okay, same thing here. This is a yes for the same logic. This one, though, is a no, and here's why. Because the absolute value of x, the square root of x is really x to the 1/2 power, which is not a whole number. So because this exponent, because absolute value of x is, because the square root of x is x to the 1/2 power, this is not. Because all powers must be whole numbers. Let's say whole, okay? So yeah, you won't really have to know this, but just for the future, to know which one is and which one is not, and if there's any sort of tricks. Okay, moving on a little bit, we have this one where we're just multiplying these two polynomials. Mr. Jacobs, when he made this, was nice enough to give you the area model, which you do not have to use. Really, what you have to remember is that you're multiplying everything in this first one. You multiply everything in the first parentheses to everything in the second. So I need to make sure to hit everything in the original set, this sort of x cubed one into this x minus 2 one. And the best way to do it, in my opinion, the best way to keep your thoughts organized is to use an area model, this little box. And you're kind of like reverse foiling. Like you already know what goes on the edges. And so, or not reverse foiling, reverse factoring. You already know what goes on the edges. So like I'm gonna put my x and my minus 2 from this. I'm gonna put my 2x cubed minus 3x squared plus 1x plus 5 up here. And then what I do to fill out all these boxes is just multiply these two things together. So I just find 2x cubed times x is 2x to the fourth. 2x cubed times negative 2. Well, negative 2 times negative 2 is negative 4. And then there's no x here, so this is just x cubed. And then we keep going. X times negative 3x squared is just negative 3x cubed. This one's nice because it's just going to add an extra x up into the exponent. This one, though, is going to just double it and make it negative. So this one's going to be positive 6x squared. This one's just going to be x squared or 1x squared. And this one's going to be negative 2x. X times 5 is 5x. And 5 times negative 2 is negative 10. And if you set it up correctly where everything's in order, then what you have to combine are always these diagonals going across like this. Which is kind of neat. Okay. And so I'm going to write it out long form, and then I'm going to combine everything together after. And so really what I have in its longest form is this. 2x to the fourth minus 3x cubed plus, or I'll say minus 4x cubed. So I'm going to go like this sort of like wrapping pattern, I guess, plus 6x squared plus x squared minus 2x plus 5x minus 10. Okay. You don't have to take this step where you do everything out. You could just combine these before writing the answer. But now that I have it written out, all of these sort of sets of two are going to combine together. These are all like terms, and so we can simplify. And so our final answer is going to be 2x to the fourth. And then minus 3 minus 4 is minus 7. X cubed. 6 plus 1x is 7. X squared. Negative 2 plus 5x is plus 3x, and then minus 10. And there's your final answer. Okay, so you don't have to use the area model. You can just sort of distribute out like this, but just make sure you hit everything. I was working with Jace yesterday in Homework Center. We were doing this problem exactly, and I used the area model, and he didn't. And he messed up, and I didn't. Okay, here we go with number 27. This one, we've done practice problems, and this is the one that you did on my door, if you remember that review day before our previous test. But you just have to kind of tell me what's going on with this function. There's a little bit of a scale, so you could make up some numbers here. But really what I'm going to do is just figure out these main points, what's going on, okay? So y-intercept, I can see that across my y-intercept at the origin. So that's at y equals 0 or the point 0, 0. Okay, it's not bad. Then the degree of this function is a little bit more tricky. We have to think about, are we crossing through the axis or bouncing and then counting up how many times that happens, okay? Well, I know based on the shape of this, because of its end behavior where both tails are going up, that this is going to be an even degree function before I even know what degree it is. And this could actually be a couple different degrees. So as long as you give me something that's reasonable, that'll work. And here's what's reasonable. If I cross through right here, that I'm going to assume that that has a multiplicity of 1. So I crossed through at this point. That means I have a multiplicity of 1, okay? And then at this point, I actually bounce through, which means I have a multiplicity of 2. And then at this point, once again, I cross through, which means I have a multiplicity of 1 again. If I add up all my multiplicities, just like I was in factored form looking at the exponents, that would be my degree. 1 plus 2 plus 1, 1 plus 2 plus 1. I don't know why I wrote plus first. 1 plus 2 plus 1 equals 4. So that's my degree, which is an even number, okay? And then based on the end behavior, I know that both tails are going up as x goes to the left and right. That means it's concave up like a cup, which means it's happy. So it is a positive leading coefficient, right? The a value is positive because my shape generally is going up on both ends. Domain and range, well, we do have a new way to write domain and range, which is kind of cool. So let's do it in interval notation. Remember, domain is all your values left to right. It's all your possible x values. And even though these tail ends are getting more slanted, they are in fact continuing on to the left and to the right forever. It just takes them a very long time, but luckily with domain, we care about every single possible point. So negative infinity to infinity, which our lines could meet, right? These lines do extend out this way. So give it enough time, it will reach negative infinity. And then this tail end will also reach positive infinity. So that's my domain. The other way to write that is all real numbers like that. Okay, it's everything. Our range, however, is not. Our range is all your values top to bottom, all right, or bottom to top. And I actually have a lowest point. It's right here, right? My absolute minimum is right here, which if I look at this scale, I'm going to say is like, this is 1, 2, 3. So let's give it like a 2.9, I guess. I don't know. I just made that up. You don't have to be perfect. You could say 3 if you wanted, but I'll go with 2.9. Negative 2.9, that is. And that's the lowest point I can get on my graph. And so I know that my absolute minimum is actually at negative 2.9 in the y. I guess I have to figure out the x value for that. Let's say my x value is like 1.5. So my absolute minimum is 1.5, comma, negative 2.9, I guess. And my absolute maximum is nothing. There's no absolute maximum. This can go on forever. So no absolute max. Really, it's infinity, but that's not a number. And then your range is just your lowest value to your highest value in terms of y. And so my lowest value was negative 2.9. And this time, which is kind of cool, is I can actually hit negative 2.9, right? And so this is the first time we've done it, but I can actually use a bracket here in my interval notation because negative 2.9, as I've defined it, is actually one of the values. And so I write negative 2.9 with a bracket because I can include it in my interval to positive infinity with the parentheses because I can't include infinity. All right, we got a few more. Write an equation in factored form for the polynomial. So here's what you have to do. You kind of have to reverse engineer the problems with the different components. So we would write a factored form, meaning we want like x minus something times x plus something or whatever. But in order to find what we are adding or subtracting, we need the zeros. And so I have a 0 right here that I cross through at x equals negative 1. Okay. So that means that one of my points or one of my factors is going to be x plus 1 to the power 1, right? Because I'm crossing through it. And then I put plus 1 in my actual equation because x is negative 1 and that makes it 0. So the point at which it turns to 0 is negative 1. And so in my equation, I need the opposite, x plus 1. Okay. And then my other 0 is at this point, which is at x equals positive 2, and I'm actually bouncing through it, which means I should have a x minus 2, because that would make 2, x equals 2, make this function 0 to the power 2. And then the only last thing to check, which you actually don't have to be perfect for, because I did say an equation, which means you could have this in various ways, but we do have the scale to find the y-intercept, and I think it just so happens that this function works out. If I plug in x equals 0, I'll just get 1 times negative 2 squared, which is 4, which is this point. So I think this is not only an equation, but the exact equation of this line, which is pretty dang good. Okay. So there you go. Use the zeros to figure out what you put in the parentheses, and then use the fact of whether they cross or bounce to make their exponent or their multiplicity. Okay. Let me make sure I've been recording my voice. That'd be so embarrassing if I wasn't. Okay. Sketch a polynomial. Oh, I love these problems. So we just put the points down and then think about the only way to fit that, okay? We don't have to write the equation or it for anything. We just have to plot the points. So x-intercept at -1 is like right here. We'll do that. So that's at -1. And it has a multiplicity 2. So I'm going to bounce through that. And then I have an x-intercept at 4. So that's 1, 2, 3. It's like here, I guess. So we'll say this is x equals 4. And this one's going to cross through because it has a multiplicity 1. So this one's going to bounce because it has a multiplicity 2. This one's going to cross because it has a multiplicity of 1. I have a y-intercept at -2. So that's right here. So it's -2. So that's another point. And then I have a positive leading coefficient, which means either way, I know that I'm going to start. Let's see, what is this going to be? This is actually going to be odd because I need to bounce off of this and cross through my y-axis, which means I need to start from down here, come up, bounce off of this 0, go back through my y-axis there, and then head towards this point and then cross through it. Oh my goodness, that was one of the worst lines I've ever drew in my entire life. Let me try it again. We go bounce, cross. Oh, my hand slipped. Let me try again. Oh, I did it in one stroke. Okay, let me try it. Bounce, cross. Don't let my hand slip. Oh, there you go. That looks amazing. Kind of. Not really. But that's got to be it. Another way to figure out like where to start from, I just started down here because I knew I have to bounce off this one, and there's no other zeros to the left or to the right. So the only way to bounce from this and still be underneath the graph is to start down below. And then also I know that adding up the multiplicities, 2 plus 1 gives me an odd with a positive leading. So I know that my end behavior with both of these combined is going to look like that, which this one kind of does, just with more squiggles. Okay. 30 and 31. This one's like a Mathia problem. We didn't really do these, but I bet we could do them fairly easily. I think the reason I didn't do them is because, well, that Mathia workspace was a real toughie. But really all you're thinking about is if I want to expand out my deck to have these new dimensions, my original deck was 20 by 15, and now it's going to be 20 plus x by 15 plus x. And so my equation is really 20 plus x times 15 plus x, okay? And that's equal to my area, okay? But I know that my area is equal to 200 because that's what it says in the problem. And so really this is my equation, and I can actually solve for this probably using the quadratic formula. If I multiply this out, let's see what happens. So I'm going to FOIL this out, or just binomial expand it. And I already did that one. I got to do 20 times x and x times x. Okay, so I'm going to get x times x is x squared, 15x is 15 times x, 20 times x is 20x, and then plus 15 times 20. Oh, I can't do that in my head right now. 20 times 15 is 300. Okay. That can combine to this. So x squared plus 35x plus 300 is equal to my area, which is 200. And if I want to use the quadratic formula, then I can subtract 200 from both sides. And I get this equation, x squared plus 35x plus 100 equals 0. In fact, both ways, like if you want to factor this or use the quadratic formula, you have to make sure that your whole equation is set equal to 0. Let's see if we can factor this. So we have to find two numbers that multiply to 100. That's a times c, but add to 35. What is that going to be? 25 times 4. No, not 25 times 4. 20 times 5. Does it have nice factors, do you think? Or they're going to be odd numbers? You might be even able to do this in your head if you think about just the area calculation. Let's just use the quadratic formula. So A is 1, my leading coefficient. B is 35. And C is 100. And so for the quadratic formula, x equals negative 35 plus or minus the square root of 35 squared. Whoa, that's big. Minus 4 times 1 times 100. Yeah, I feel like this is not going to be a nice number, but let's see. All over 2. Okay. Another way to do this is to graph it and find the minimum, or the x-intercept. But ooh, someone commented on my YouTube video. Here we go. So I'm going to plug this into my calculator here. Let's bring it up. So let's go x equals, and then parentheses, negative 35. Let's start with the plus. The square root of 35 squared minus 4 times 1 is the same. So just 4 times 100. Oops, I messed that up. 4 times 100. Close parentheses because I'm going to divide by 2. And so my first answer, yeah, is not 9. Wait, what? That shouldn't, wait, what? Negative 35 plus 5? Oh, because I'm going to have an extraneous solution. Wait, no, there's no way. Wait, what? Huh? I'm super confused now. What's 35 squared? Minus 400. Second answer, or square root of 825 is 28. Huh. What did I do wrong? Oh, I read the problem wrong. It's going to increase the total of the area by 200. So this isn't equal to 200. It's equal to 20 times 15, which is 300, plus 200, which means that my total area is 500. I'm sure someone was staring at the screen or yelling at the screen doing that. Which means on this side, I have 500. Yeah, this is going to work out better, I think. And so I'm subtracting 500 from both sides here. 500, 500, which means that my C value is actually going to be negative 200. Which means in my equation, I put this here. And that's going to give me some positive numbers. Okay, let's retype this in then. So we can go back up to this, I think. Hit enter, and then I'm just going to try and change this 100 to negative 200, but I'm not sure if it'll work out for me. Oh, it does. That's fine. Cool. So my first answer is 5. Nice. I think that makes more sense. So x equals 5. And then I think we're going to get an extraneous solution, meaning we're going to get some negative value when I do the second half here, which isn't going to matter because there's no way I can add a negative measurement. So once I go back and change this to a negative sign, I get negative 40, but this is an extraneous. In other words, it's not important because it's negative. And I can't have a negative number in real life or a negative value in real life. And then that totally changes my factor thing too, which we maybe could have done in our heads that way, but there you go. Okay, so x equals 5 is my answer. So that means that x must be 5 feet longer. So 5 feet. Sorry about that. That's why you got to read the problem, okay? Cool. Do not actually divide. Would you use polynomial long division or synthetic division to divide these polynomials? In my opinion, in fact, the only way is to use polynomial long division, and here's why. Because the term of my quotient, divisor, the thing I'm dividing by, which is x squared plus 13, is not in the form x minus r, which you need to have for synthetic division. Now, it doesn't have to be like exactly x minus something, but it has to be at least a power 1, right? So because my thing that I'm dividing my divisor is degree 2, I have to use polynomial long division. So because the term of my divisor is not in the form this, I have to use PLD, polynomial long division, because of the x squared. Okay, so let's actually do it now. Now we have an actual problem to do, and I'm going to try and keep this as, let's try and do this as nicely as possible. Okay, I'm going to try and keep my thought process perfect here. Okay, nice and neat for Kendall. Okay, so x squared plus 3 is what I'm dividing by, and then what I'm dividing into is this whole thing, 2x cubed plus 9x squared minus 12x plus 15. I'm going to shift this down just a tiny bit because I'm going to write my answer up here. Okay, so to recall the steps, first what you got to do to find this number, to find what you're putting in your first term up here, is you got to figure out x squared times what gives you 2x cubed. Okay, so you take the x term, you figure out what you multiply it by to get the first term inside of your sort of division thing here. Well, in order to turn the x squared to 2, I have to multiply it by 2. And then to turn the x squared to x cubed, I have to multiply it times x. Okay, so once you find this, you then actually multiply. You multiply this, the 2x, times your whole divisor, and you write it right here. So it becomes 2x squared, or 2x times x squared is 2x cubed, and then 3 times 2x is plus 6x. Okay, sorry about that. Yeah, so I actually multiply it out, and then this time, which is kind of weird, I get this 6x, right? This 3 times 2x is not actually an x squared, so I'm just going to write the 6x over here, and then I'm going to actually subtract everything. And so really I'm putting like a plus 0 in between, and then you subtract your whole line, and you subtract it from what's actually above it, okay? So, whoop, you actually subtract 2x squared times, or 2x cubed minus 2x cubed is 0. 9x squared minus 0 is just 9x squared. And then negative 12x plus 6x, or sorry, negative 12x minus 6x is negative 18x. Okay? And so even if you have to skip one, you just kind of keep going along the line. And then this is your new starting point, this 9x squared. And so your next term up here is going to be, what do you have to multiply this by to get to this, which is plus 9, okay? And so then you end up getting 9 times this whole thing, and that's what you write here. So you say 9 times 2x, or x squared is 9x squared, and then 9 times 3 is just 27. And so in this case, you just drop this down, put a 0 here, and then this 15 is what you're subtracting 27 by. And so we're going to end up with a weird remainder, but it's actually going to be okay. So after I subtract these, I'm really canceling these out. Negative 18x stays because I'm subtracting 0 from it. And then 15 minus 27 is negative 12. And now, because my leading term of my divisor is x squared, there's no way to multiply into this. And so I have to stop here. This is actually my remainder. This is my remainder. And so in total, my equation, this whole thing, is really 2x plus 9 from what I found to multiply in, plus my remainder, which is this term, negative 18x squared minus 12 over what I was dividing by, x squared plus 3. Okay. So this is a weird one, actually. We have to skip some terms, but it all works out in the end. It just leaves us with a weird remainder. Okay. Let's do the synthetic division one. Okay. So the thing about synthetic division is to note that we're kind of flipping around our idea. We're kind of finding zeros instead of, or like dividing this in and trying to find a 0. And so what we're using to divide, or our synthetic sort of key, the thing that we're using at each point is the value of x that makes our divisor 0. And so really we need to know x equals 2, and that value is what we put right here on the sort of outside of our synthetic thing. And then what goes here is all the coefficients in our polynomial. So 1 for 1x squared, minus 5 for negative 5x squared, plus 9 for 9x, and then plus 1. I don't have to write the pluses, okay? And then we're going to do this process a bunch of times, and at the end, we'll have the coefficients to our final answer, okay? So first things first, you always drop down this first term, and so you just put 1 here. And then to find this, you take your sort of R value is what this is called, and you multiply it times whatever number's here. So this is 2 times 1, which gives me 2. And then you add these up. So negative 5 plus 2 is negative 3. And then same process. You take 2 times negative 3, so negative 3 times 2. That gives me 6, negative 6 that is. So I put negative 6 here, and then I add. 9 plus negative 6 is also negative 3. And then I multiply again, negative 3 times 2, and I get negative 6 again. And then I add. And so my remainder is 5, negative 5. Okay. Oh, wait. 9 plus 3 is positive 3. Or 9 plus negative 6 is positive 6. So this is actually, sorry. This is positive 6, because it's just 3 times 2. And so 1 plus 6 is 7. Okay. So here's what you do. At this last term right here is your remainder. And then all of these terms are the coefficients of your polynomial. Since I started with x to the third power is what I was dividing, and I divided by x to the first power, that means my first term in my final answer is going to be an x squared. And you just put the coefficient in front. And so this is just 1x squared minus, and then you work your way down, 3x plus 3. And you know that you have your remainder because you're out of x's, right? Like I can't keep working my way down. And so I know that this has a remainder of 7, which means it's plus 7 over what I was dividing by, x minus 2. And there's my final answer. Okay. Keep going. So with this one, really what we have to do is factor our top and bottom. This is just a rational thing. On the test, this will be bonus, the horizontal asymptote. And so really all you need to know is the holes and the vertical asymptotes, which are your domain discontinuities. Anytime that your x value stops, okay? And then your horizontal asymptote, I'm going to talk about how to find it, but it's a bonus question on the test, okay? So let's factor these. So I'm going to start by factoring the top. So the top goes like this. I need to multiply to 6, but add to 7. Anytime you see this sort of pattern, it's going to be just 6 and 1, or whatever multiplies to that times 1. So my factor on the top is going to be x plus 1 times x plus 6. And then on the bottom, I have kind of a similar thing. I have multiply to 4, but add to 5. That's got to be 4 and 1. So my bottom is x plus 4 times x plus 1. Okay, so that's really my new polynomial here. I factored out the top and the bottom. Oops. And then what I notice is that I have one polynomial on the top that's also on the bottom, which means I can theoretically just cancel these out. Okay, and so in final, my polynomial that I'm really looking at and what it's visually going to be is I'm going from x plus 1 or x plus 1 times x plus 6 over x plus 1 times x plus 4. These are kind of canceled out theoretically, but that's going to create a hole. Okay, So a hole happens when you cancel a factor, but there's a value of x that makes it 0. Okay, so what that means is visually, my graph, like you've plugged this into Desmos, it would look exactly like this, which we'll talk about what it looks like in a second. Okay, but there's only one thing that's different. Even though I cancel these out, I have to keep remembering them if I were actually plug in values. And if I plug in the value x equals -1, I'm going to break my function because up top, I'm going to have -1 plus 1, which makes my entire numerator 0. And on the bottom, I'm going to have -1 plus 1, which makes my entire denominator 0, which means I'm dividing 0 by 0 when x equals -1, and that causes a hole because that is when I canceled the factor, but -1 was the value of x that makes it 0. Okay, so there's a hole at x equals -1. Anytime you'd have 0 over 0, that means there's a hole there. Okay, a vertical asymptote happens where you would just divide by 0. So in other words, the vertical asymptote is what happens when, or what values of x make the function 0. Wait, the function 0? The denominator 0. Denominator equal to 0. We already have our whole sort of canceled out. So the only value of x that makes this equal to 0 is when I plug in -4. So x equals -4, because that'll make the denominator equal to 0. If the denominator is 0, then I'm dividing by 0, which means I have an asymptote there, right? My equation's going to break. Okay. The horizontal asymptote. The horizontal asymptote. Oh, I'm sorry. I'm running out of note space. The horizontal asymptote happens when, well, you have to take the leading terms. It's the ratio of the coefficients of leading terms. Okay. Remember, this is bonus on the test. But what that means is, because my equation has x squared over x squared, those are my leading terms, right? My initial function, my largest degree terms were x squareds. This is just 1x squared over 1x squared. The ratio of the coefficients is just 1 over 1, which means that my horizontal asymptote is at y equals 1. So you just divide what's in front of your biggest exponent term, or the leading coefficient. Okay, so since they were both x squareds, you divide 1 by 1, and you get y equals 1. Okay. The x-intercepts happen when the numerator is 0, right? When the output would become 0, because that's what an x-intercept tells you, right? And so in this case, it's what happens to make x plus 6 equal to 0. So that means that it's at x equals -6 or -6 comma 0. Okay. And then the y-intercept happens when you just plug in 0 for x, which in this case would just be 6 over 4, which is 3 halves. Okay. I believe the x-intercept is also bonus on the final. Okay. But cool. I know we just kind of talked about this, but you will have access to a graphing calculator as well. So don't feel like you have to memorize all this stuff. You can plug this into a graphing calculator and find the discontinuities from there. Okay. On the actual test, you might need to actually write the domain and range. So I'll do that real quick right here. Remember, your domain is all your possible x values. And so it's any place left to right where I get stopped is where my domain is going to get stopped. And my two discontinuities happen when x is -4 and x is -1, which means my domain looks like this. I can go all the way to the left, -infinity to -4, union, -4 to -1, union, -1 to infinity, right? That's any place I can go left to right. And then my range, I know the only value that I can't get to is where my horizontal asymptote is. And so it's just -infinity to 1 and 1 to -infinity. Okay, or positive infinity. Okay, cool. We got 2 more problems to do. This one, once again, we're kind of doing the same thing. And here's what it would look like. So once again, I'm just going to factor the top and the bottom. And so I end up getting x plus 3 times x minus 3. This is a difference of squares, which I talked about in the last video. Okay, difference of squares. And then divided by, I actually have to factor the bottom. So here's what the bottom looks like. It's multiply to 18, add to 9. That's got to be 6 and 3. So this is going to be x plus 3 times x plus 6. And let's use the same logic. So I can basically kind of cancel out this set of parentheses right here because there's the same thing on the top and the bottom. However, that creates a hole at that x value that makes it 0. So when x equals 3, I have a hole there because I'm canceling these out. My vertical asymptote happens whenever my denominator would be 0. And so that's when x is -6. My horizontal asymptote is the ratio of the leading terms, which once again is just x squared divided by x squared. That's 1 over 1 because that's 1x squared and 1x squared, which is 1. So I have another horizontal asymptote of y equals 1. The x-intercept is going to happen at x equals 3 because that is where my numerator is 0. And then my y-intercept is what happens when I plug in 0 to my function. That means I get -3 over 6, right? I'm just writing out these 2 polynomials that's left from this, x minus 3 over x plus 6. To find the y-intercept, you just get rid of the x, you make it 0. And so I just have -3 over 6, which is -1/2. Okay, cool. Factor this polynomial. I'm about to run out of time. The bell's going to ring. So I will do the final 2 problems in class today. Otherwise, I think you can actually do these last 2 pretty easily because we've talked a lot about making these ratios. For these ones, just find the common denominator. And really, the common denominator for these ones is a lot simpler than the ones we've been doing in class. Okay, so you should feel comfortable on these. If you need extra help, you can come talk to me today, or I guess on Friday. And then to factor this polynomial, the only thing you need to remember is to use the box method. Okay, so you actually have to find what a times c is and what b is. In this case, that would be 10x squared and 11. So 2 numbers that multiply to 10x squared, add to 11x. That's going to be 10x and 1x. And that means I have to go. But let me set up the area model real quick for you. You would put your leading term here, 5x squared, your second term here, 10x there, 1x there. And then you have to figure out what these edges are. And once you do that, you have your factors. Okay, sorry to cut it short, but that's it. So thank you guys for watching, and I will see you in class.